and I would hand over to our next presenter, which will be Gregory. And finally, we are getting some insights about radiation testing. And yeah, Gregory will give us an introduction about, or let's say a presentation about best practices for protons and heavy ion testing. Our speaker, so Greg has spent the last 20 years working on radiation effects fields, focusing on single event effects accelerators, spending most of his time in accelerated testing of electronics for the use in a natural space environment. Greg received his bachelor degrees in computer engineering from the CHU, Chicago, and MSc in the system architecture and engineering from the University of Southern California. Greg is a senior radiation effects engineer at the Jet Propulsion Laboratory, California Institute of Technology. And Greg is the co-lead of the JPL Laboratory Center for Space Radiation and the group lead of radiation effects. So with that, we are looking forward to your presentation about best practices for SEE testing with focus on heavy ions and protons.
Thank you, Jan. I appreciate the introduction and thank you for having me out. Serendipitously, I'm actually presenting from an accelerator today. So we have beam time this week, and I'm going to hustle through this presentation and jump off and get back to testing. But it's a pleasure to be here and speak to you all today. As Jan mentioned, I'll be talking about some single event effects testing best practices for heavy ions and protons. Okay, there we go. So I always kind of like to start with the big picture. So why do we do SEE testing? What's the purpose of SEE testing? And I think the previous presentations gave a good foundation for all of this. But just to reiterate, we perform this testing to understand two things: reliability and availability of our system in a given environment, right? And so to do this, we need to understand two things: the environment of interest, and we saw a great talk on that earlier today, and the device sensitivity. And to understand device sensitivity, we need to perform testing and develop a cross-section versus LET for heavy ions or energy with protons curve. And we convolute that with the environment and understand the impact, both reliability and availability. But another way to look at it is, why do you as an individual SEE test? And this is important because the advice that I provide in this presentation and the way that you interpret guidelines and requirement documents are going to be very dependent upon your perspective and what you're trying to accomplish, right? And from that perspective, you may be a manufacturer performing qualification or developing future products. You may be like myself as an end user, trying to perform testing for radiation hardness assurance of spacecraft design. You could be part of an accelerator, trying to develop rad-hard systems for accelerators, or working in strategic environments. And you may be a researcher or in academia, looking at rad-hard by design or by process, looking at dosimetry or future technologies. Likely you're a blend of a few of these different things. The point is that depending on where you're coming from, you're going to have different test approaches and different test goals, and have to look at requirements in different ways. And the other thing is, how are you testing? And each of those roles may have a different kind of test approach depending on where you are in your test cycle or design cycle, right? You may be performing go, no go testing, where you're just quickly trying to evaluate a device or a set of devices to down select to the best performing one. If you have a single device in mind, you may be performing a screen to a given requirement if you have requirements set already. Typically, this is a destructive SEE or DSEE. You may be fully characterizing a part, again, looking for soft errors as a function of LET, so developing that cross-section versus LET, or testing to worst case conditions or corner cases. Or you may be performing full qualification, especially as a manufacturer or vendor of technology, right? And there's no one right solution here, again, and you may evolve through different solutions as you're improving your understanding of a given technology through testing. And so there are documents that exist. There's a set of references in the back of these slides that will be available to the audience, but I wanted to put them up here quickly. I'm not going to go through them all. And this is not comprehensive. There are others. These are kind of the ones that I wanted to point out. But because, as I mentioned in the previous slides, there are lots of different approaches. There are lots of different perspectives related to SEE testing. A lot of the information and guidance in here is what I'll call a rule of thumb or a generality, right? And so if you interpret those and take them on and follow them, then You're going to get data, you're going to get good data. But where you really excel as a radiation engineer is knowing how to violate those rules, how to bend those rules in order to have, um, in order to interpret results and get the kind of test results that we need for your programs, right? And so that's really the key, is not just what to do, but why are you doing it, right? Understanding the why behind the what is really, really important. And so I challenge you to take that upon yourself and look at that, look at in that perspective. I'm briefly going to talk about a test plan. Several of those documents I provided do talk about what to go into a test plan, but I'll say again, you want to begin with the end in mind. It's a Stephen Covey quote, habits of highly effective people. But again, what are you trying to accomplish in this test? That's where you really start when you're starting the test plan. And then you have your 3 Ps: know your purpose, know your part, and know your particles. So your purpose, what are your test requirements? What are your test goals? Globally, individually, what are the people on your team supposed to be doing? What are their purposes? What are the roles and responsibilities of everything? Know your part. What's the technology? What's the process? What mechanisms are we, that helps define what mechanisms we're looking for and tie those mechanisms to requirements, sample size, etc. And particles. Given our requirements, what are the ion species and energies that we need to achieve those requirements? What's our approach? Where are we going to start in LET? What's mapping out the ion change plan, depending on what we see, and then make a cheat sheet, right? Sometimes we'll be testing a dozen different parts in one test, and we don't want to have to go through, a 12-page test plan. And so cheat sheets for all of those are a handy way to remind ourselves what the really important things are for each of these types of components. And then we all know that one of the first things that happens when we start testing is that we throw out the test plans. But I got this quote down below from Dwight Eisenhower. In preparing for battle, I've always found that plans are useless, but planning is indispensable. In spite of the fact that we know that things are going to go sideways quickly and we'll have to pivot from our test plan, the act of planning is really, really important, right? Going through the exercise of thinking through your experiment is invaluable. All right, so a little bit more about know your part. Read the data sheet. That's the first thing. End to end, it's important to know exactly how this part works. As Michael was saying, engineering best practice is important for system design. It's also important for radiation testing. And so one of the most valuable things in a data sheet is the block diagram. This gives you insight into tying process to functionality, right? So let's walk through a little bit of that. I'm not going to go to all of these for brevity, but if you see the thermal shutdown block there, likely what that is a comparator that's comparing the junction temperature to some set point. And so in your mind, you can think through, well, if a transient hits that comparator and triggers a shutdown, I'm going to go to probably a low current state. I'm going to lose functionality. That may require a power cycle. It may have a reset mode, etc. But I know what I'm looking for when I start testing. The other thing is, because it is a comparator and is sensitive to the input voltage of that comparator, higher temperatures will likely trigger that event more often, right? So typically we think of latch up as the one mechanism that we really want to worry about being temperature sensitive, but functional interrupts can be temperature sensitive as well. And thinking through that, if this is a functional interrupt that impacts your system, you may want to be looking for that and measuring that at higher temperature, right? Or bookending the range of temperature in your ConOps. Same thing with overcurrent protection, right? Except now we're load dependent instead of temperature dependent in that shutdown mode. I'm going to skip over some of these, but I want to point out that there are DMOS or MOSFETs inside this part, right? And so here, where we have to worry about latch up in the control logic, we have to worry about transients and Cepheid modes in the components that I spoke about, and then over here we have to worry about burnout and gate rupture on these DMOS, and so and shoot through. So we have three or four different mechanisms that can result in permanent device failure, right? We have latch up, we have SEP or SEGR, we have shoot through, and so we'll have potentially different LET, different derating requirements for each of those mechanisms. And so we need to develop a test plan that can identify any of those mechanisms and understand what the failure sensitivity is for each of those, right? So we can tie them to our requirements and derating appropriately. And all this comes from a block diagram before we even test. Part construction is another really, really important piece of planning and test execution. Typically, we're starting with an X-ray that tells us a lot. Tells us if there are multiple components, is it hybrid? It tells us the bond wire construction type, where the die is, et cetera, and gives us information about how to depackage and get to the transistors of interest. Just to point out, the ions that we use terrestrially for testing are typically a much lower energy than the ions in space. And so we have to remove material in order to get at the areas of interest, the sensitive areas. A good trick is to always track pin 1, either with a photograph or with marking with a marker, because once we remove the package material, we may lose track of that. Also plan on not having perfect yield in depackaging. And so buy more parts if you can afford it, and if they're available, than you need for your sample size for testing. Physical cross-section, as you can see on the bottom right, can be informative to look at stack up and material thicknesses. And then that was mostly for heavy ions. And then for proton testing, we want to know part construction. Are there high Z materials, right? And so that kind of dictates LET threshold from a heavy ion perspective. What we have to worry about in terms of if we have heavy ion data and we're looking at proton data, or if we need to do proton testing to understand proton sensitivity, right? And simple transport, if we have a lot of material, like you see that large inductor, you see a large stack there, making sure we go through the exercise of performing a energy transport through that stack up. Another thing, I'm on device preparation. That was mostly for face up or bond wire up type devices. For flip chip devices where the silicon substrate is on the top towards where you'd be testing towards the beam, uniformity is important. So we have to mechanically thin the substrate, and there can be variability in that. You see the heat map there where you see up to 20 microns delta in the part thickness. This results in a difference in LET. And so understanding those differences in LET, tracking that with error bars, as you can see on the plot on the right, we have Y error bars for our measurement uncertainty. We also have X error bars for our LET uncertainty. That's very important. And also to ensure that we're not ranging certain ions out. So ion selection can be informed there as well. So once we know our part construction, and assuming we have our requirements, at that point, we can determine what facility to go to do our testing. In my mind, there's a couple of first order things that we think about when we're considering a test site. And really is just the number one thing is, where can I go to get the LET that my requirements dictate I need to get, given the part construction, right? Sometimes we have parts where we can fully deconstruct, we can etch out the plastic package, or we can remove heat spreaders and thin silicon substrates and get at the area we need to. Sometimes we can't, and that necessitates much higher energy facilities, right? So once we have that and we've pinned down exactly what facility we can go to achieve our test requirements, where can you get time? That's usually the second driver. We know that test facilities are in high demand, and it's difficult to get time there. And so we'll have programmatic needs, we'll have schedules, and the down select process usually moves to that next. What gets me the test on the schedule that I need to get it. Secondary considerations are beam structure, the difference between synchrotrons and cyclotrons, a continuous beam versus a pulse beam. There are business and operational differences in terms of how long it takes to get a contract in place, et cetera. And so, all of these considerations are also important when you're considering where to go. A little bit about sample size. These are general recommendations. So for characterization, we recommend at least 3 parts. That's the general rule for SEE, is we want to have 3 parts, absolute minimum of 2. Sometimes you have to come in with 1 because that's all that's available. I also want, while I keep talking about sample size, I also want to give an opportunity. This is the beamline at Texas A&M. For those of you who haven't seen a cyclotron test area or accelerator test area, there's Sergey setting up. So you have a target room down below. There's a distance between the target room and the data room. See that's there. We're heading up here, and then we head over to the data room, right? And we'll see more of this in terms of the test setup in a moment. But a little bit more on sample size. Sample size of 3 for compliance qualification is necessary. But if we're not doing qual and we're having destructive failures, you can see kind of on the bottom right there with those GAN devices, you want much more samples, right? If we're doing fluence to failure and they're destructive, we need more samples to develop a safe operating area for that technology. And then in terms of efficiency, having a DUT board that has multiple sites, so you're not going up and down those stairs that I just showed 300 times every time you want to switch out a sample is important for beam time efficiency as well. All right, so if you have your plan together, you've deprocessed your parts, and now you're ready to do a checkout. Right? So it's really important before you ship out and head to one of these facilities that you test with the exact set of cables that you plan on testing at the facility. You saw in that video that there's a bit of distance. It could be anywhere from 10 meters to 30 meters between the target room and the data room. And so you want to test with the exact cables you plan to use at the facility. You can use fault injection techniques, flash strobes, pulse lasers, alpha sources, etc., to put errors into your system to ensure that you're capturing data correctly. And then a test readiness review, whether it's a formal test readiness review with management or just having someone else look at your setup and walk through the experiment is really important as well. Sometimes there's a forest and trees problem and you're so focused on certain parts of the test, you miss other parts in the big picture. So it's good to talk through somebody else and think about what you're doing. Real briefly on shipping, I know that this seems kind of like a silly thing to talk about, but according to Dr. Henry Clark at Texas A&M Cyclotron, shipping issues account for number one reason people drop beam time. Stuff just doesn't get there. So pack early, ship early, give yourself twice as much time as you think you'll need. Anticipate if there's going to be weather or holiday impacts to the shipping, and then take care of your parts. Right, we've depackaged these parts. We've got exposed bond wires. Make sure that you pack in a way that things won't get damaged while you're shipping. And then you also want to give yourself time when you get there in case something does happen. So give yourself an extra day. Get to the facility early. Pretty much every accelerator has a setup area. Share that space. There may be other users, and so don't spread out and take over every bench. And then communicate. Communicate is really, really important. When there's a time for the users that are on the beam at that moment to talk to them, ask them how things are going, ask them if any of the ions are causing trouble, what the flux of certain ions are. Talk to the operators. This all informs efficiency, right? What are they going to end with? Maybe you can pivot from your test plan and start with what they end with so you can save some tuning time, etc. So be sure to communicate with people when appropriate. I mentioned roles and responsibilities earlier. It's really important to know who's doing what, right? And so here's a typical set of roles. Your team may have all of these, may have none of these, but this is kind of how I think about things. You have an experimental lead. This is typically the person who designed the hardware, firmware, and/or software. They're responsible for the test setup. It doesn't mean no one else knows about the test setup, but there's a lead on that. You may have a project lead. This is someone who's focused on the programmatic goals and requirements. Typically, they're doing on-site data analysis and making sure that the testing that we're doing is meeting the big picture goals. Sometimes you'll have a technician in place because something is going to go wrong. You're going to need to solder off a blown cap and replace it. You may need to swap parts out, etc. Sometimes that's me. You need to know how to solder at the beam. So having someone who at least can get their hands dirty and work on hardware is really, really important. Often, we'll pull outside of our radiation effects organization and pull in a designer. This is someone who's either working on a system or a technology day after day, and they're really embedded and understand things well. And so that's really great system perspective, right? And technology perspective that we as generalists who need to test hundreds of parts a year may not have that depth of knowledge of that technology. Briefly, the test setup. Here's a block diagram of what a test setup may look like. So again, down in the SCE test cave, the target room, you'll have all your general support equipment. We'll remote in via laptops, typically with Ethernet, USB, GPIB, whatever the communication protocol. We'll have power supplies, oscilloscopes, temperature monitoring, ways to create heat or cooling on our test devices. A couple of other tips: run all the cables at once. Typically, there's a small pipe that you need to run things through. Once you start putting things in there, it gets difficult to run additional cables through. So even if it's a test that's 12 hours away, go ahead and run that cable now. Again, know who's responsible for what, roles and responsibilities. For protons, you want to protect your equipment, right? We'll have secondaries in the room. And so typically a facility will have some kind of neutron absorber. These could be boarded polyethylene sheets. And so you want to build an igloo around your equipment because, if you have a $100,000 scope, you don't want that failing in the middle of your test for a lot of reasons. One, you won't get your test data. Two, that's an expensive problem to deal with when you get back home. But also be careful when you're doing that you don't cause your equipment to overheat. Mounting is always underestimated, something that people often don't think about. So have a plan to mount your part. There are clamps, there are platters. All of these things are typically covered on a facility's website. So go in ahead of time, look at what they have for you, build some of those platters or interface pieces. There's no wrong way to do this, but if you don't have a plan going in, you don't want to be spending hours trying to figure out how to mount your part on beam time, right? Wasting beam time to do that. Also anticipate if your board, like you see in the picture on the right, has a lot of protruding cables, that will dictate the air gap and energy loss as you're traveling over to your active area. Data logging is really important to log as much information as possible. So we want to do two things. We want to capture everything in its raw form, and we also want to process on the fly so we can make informed decisions. And so there's a couple of things here. The obvious things are voltage, current, temperature, etc. Of our DUT. We want the facility shutter often to know when the beam was on and the beam was off, so we know if it was during a run or before or after a run that something was happening. Timestamp everything. You want as much information downloaded so that we can revisit the experiment weeks, months, years later. Logging. A log is really your own. This is just an example, but you want, again, to kind of have all the information in one place. Facility dosimetry. So what was the ion and LET? What was the fluence? What was the flux? Etc. Information about your test, voltage, temperature, those variables that change. And then you want to be able, you have run by run, you have all this information. You want to kind of accumulate it and start to develop a story, right? So you want to start plotting things, as you can see there on the right, in situ. And error bars are also really important. So harp on that real briefly. There's a reference in here, paper from Ricker back in like 1933, I think it was. And so we use that table in terms of our Poisson error bars. 95% confidence is typically what we use. You see on the right there, that LET point at 5 or 10, the error bars. The difference between 0 events with 1E7 fluence and 0 events with 1E5 fluence is pretty significant, right? In terms of that 95% confidence. And then those 3 LET or 3 cross-section points on the right, that's the difference between 1 event at 1E5, 10 events with 1E6 fluence, and 100 events with 1E7 fluence. Same cross-section point, but different levels of confidence in terms of what that data point means and how you make decisions about changing LET and quality of your data. Real briefly, in terms of dose, we look at dose from two perspectives when performing heavy ion testing in particular. One, we don't want to overdose a part as it can influence our results. And so you don't want to put more than 80% of your known TID tolerance on the part. TID is at the facility is simply calculated by that formula there, LET influence in 1.60 minus 5 correction factor. And so we don't want to overdose the part. At the same time, we cannot use, or we should not use, heavy ion testing as a proxy for a TID test. And that has to do with charge yield problem. And there's some slides on that at the end of the presentation that I'm not going to go through, but are here for reference due to time. A few notes on flux. Typically, if I don't have any idea what the response of the part is, I'm going to start out with about 1,000 ions per centimeter squared per second and adjust from there. And so you want to select flux in a way that we're not having pileup or overlapping events, but also that we maximize our time, right? We don't want to sit there for an hour and a half on one run watching nothing happen. There are instances where the response of the part becomes that are flux dependent, right? These are typically with redundancy, designs that have redundancy, like error detection and correction, RHPD cells where we have like a dice cell, devices that have TMR or triple modular redundancy, as Michael was talking about, right? So there we need to understand the sensitivity of flux, or because in the space rate flux is much lower. We're in an accelerated environment, and we don't want to be measuring artificial events that are truly flux dependent. Thermal control, typically when we're testing, we need to control temperature and we need to measure temperature, right? Sometimes we want things to be hot, sometimes we're trying to keep them cool. There are many ways to do this. Again, there's no one right way, but the important thing is to understand the uncertainty and what it means to your program requirements. Most devices have protection, ESD protection dials. You can use that. You can calibrate that to get die temperature. You can use an IR camera. You can use a thermocouple. All of these have strengths and weaknesses. But again, the important thing is to understand the uncertainty in your measurements. A couple of notes on angle, similar to flux. We have some rules of thumb here. We typically don't test past 60 degrees, 45 to 60 degrees. The reference is there on the right and in the back for that. There are some cases where we certainly have angular and rotational dependency, again, often in either non-planar type technologies or redundant RHBD type devices, right? So doing some angular testing to understand the sensitivity and effectiveness of cosine law is important. When we're going to angle, be wary of shadowing. If you have a deep package, a die in a deep in the package, you don't want to shadow out the part. Be aware of your effective range, how much range you have as you're going to angle. And then typically for proton testing, we're not performing angular testing. There are some violations of that general rule. A few more additional best practices and I'll wrap up here. It may sound silly, but always check the beam cap. So the beam cap is there to protect the interface between vacuum and air testing. It's typically a very thin film, air mica or mylar. You pop that, it's a bad day. So we want to keep it on while we're doing a setup, but sometimes we forget and leave it on and start testing and nothing is happening and we forgot to take off the beam cap. And so have redundancy in your team, have a couple people looking for that. You may want to intentionally leave the beam cap on and do a test run of your target while we're blocking the beam. And so that's because we're in a noisy facility. You may have an impact with RF or noise from the facility, and you want to make sure what you're testing is really due to radiation and not noise in the system. And then also be your own biggest skeptic. When you see something, when you don't see something when you expect to see it, or you see something when you don't expect to see it, really think about why. Often the first thing that people do is try to blame the facility, but it's almost never the case. It's usually something with your setup. And so, you know, be skeptical of what you've done and try to think about why that may be. Good engineering design. Again, Michael was talking about this. I'll harp on it as well. You know, it's important to use the right equipment for the right measurements. It's important to think about parasitics in the system, series resistance, when to use an electronic load versus the resistive load, understanding that we're in a dynamic environment, current is changing, and you may have voltage transients, those kinds of things. And then really thinking about how low is enough in terms of LAT threshold. Again, this balance between efficiency and using time in the right way and how low you need to go in terms of your measurements. And a few more golden rules here. Number one thing is just be kind to people. It's a very stressful job. We're often running overnight, a week at a time, pretty stressful, high impact results, and tensions can get high. But be kind to each other, be kind to the cyclotron staff. This is a one big team. Everyone is working together to accomplish a goal, and things are going to go wrong. You have to accept that, and when they do, take a breath, know that you put a plan together, and communicate with each other and be solution oriented. And then the other thing is develop your SCE toolbox, right? These are papers, these are lessons learned, have them at the ready, start to develop that over your career. And with that, I'll stop. And I don't know if we have time for questions. They probably went a little bit long, but if I don't, I'll get back to my testing.
Thank you so much, Greg. Really appreciate your time. Seems that you're quite busy at the moment, so therefore I take this advantage and skip this kind of question section. Also because we are a bit behind schedule and we have 2 presentations missing. But again, thank you very much for this very interesting and very good presentation. Good luck for your testing, and I hope to see you soon.